So we're continuing along with the G proof, our rigorous mathematical proof that God exists using first order predicate logic and 5 axioms that no scientist can reasonably deny. This is video 4 out of our 9 videos, and it is entitled Crash Course in Predicate Logic, Part A, Quantifiers. We have a website at thegproof.org. I'm Mark Lawrence Donald Emerson, and I'm your teacher. And the work we're doing here is based on the work of many other people from ancient times to the present, and this predicate logic was developed by quite a few of these people on this list, are directly responsible for what I'm going to teach you today. Alright, so here's our map of all 9 videos. You can see we've finished videos 1, 2, and 3, which is why they're cyan color. And in video 3, we did a crash course in sentential logic. We're going to use 100% of what I taught you in video 3, now in video 4. So if you didn't quite understand it, you got to make sure and go back and get video 3 down. Alright, so here we are in video 4, part A of our crash course in predicate logic. And then in video 5 we're going to do part B of predicate logic, and that will complete on the left side here of our map all of the part of these 4 videos where I'm teaching you the logic you need to understand our proof that God exists. Then we'll be ready in videos 6, 7, and 8 to go on to teaching you the proof. And in video 6 I'll teach you the undefined terms and definitions in the first 3 of our axioms, which I'll justify. And then in video 7 I'll teach you the last 2 axioms and justify them. We'll talk about the consistency of the axioms, and I'll do an informal proof that God exists. Now the informal proof doesn't count, it's just to help you understand what's going to happen. And then in video 6 we'll do our formal rigorous proof that God exists of the G theorem. Okay? And finally, in video 9 we'll talk about the consequences of the proof. Okay, so here we are in video 4, our crash course in predicate logic, part A. And here's an outline of this video. So first I'm going to review the 9 rules that we learned in video 3. We'll talk about predicates and letters, variables, and sentences. Then I'll talk about the 3 new symbols we're going to introduce, which is the backwards Z, the upside down A, and the equal sign. Well, the equal sign you obviously are familiar with. Then we'll talk about universal quantifiers, the upside down A, and we'll do some stuff there. We'll do one proof there, one example proof. Then we'll talk about the existential quantifier, which is the backwards E, with some more rules, and we'll do a second example proof. And finally we're going to compare the 4 of the rules we're going to learn, UI, UP, EI, and EG, and you'll know all about those by the time we get down there. Okay, so summary of the logic rules 1 through 9 from video 3. Okay, so here we are in our video. The symbols that I taught you in video 3 are, this is not, this is and, this is or, this is if then, also we say implies, means the same thing, and then if and only if. We're not using or not in the proof that God exists, but I'm including them because they're so intimately a part of this. I don't want to leave them out. I'll use them occasionally, but not in the actual proof itself. So here's a summary of our first 9 rules from video 3. We have proof starting rules and inference rules and proof ending rules. Anyway, proof starting rules, we have 2 of those. A proof starting rule starts a new proof. We have the claim rule and then ACP, which means which comes right after the claim rule to start a conditional proof. Alright, so here's the claim rule. We write the word prove and we put anything we want by claim. And then here's, if we're proving a conditional, pink implies blue, the next line after the claim line is just we assume pink. And that's by ACP, the assumption, it's our assumption for conditional proof. Alright, so those are our proof starting rules. Now we have 6 inference rules that we learned. An inference rule produces a substantive line in the proof from things already known. Unlike the proof starting rule doesn't come from anything already known. Okay, now, and there's 6 of those, and I'll just go through them briefly here. We have modus ponens, and repetition, and simplification, and adjunction, and BC, which is biconditional to conditional, and CB, which is conditional to biconditional. Okay, and then we have 2 proof ending rules, which enable us to write a done line in box and cancel, and those are CP, which is for a conditional proof, for proving pink implies blue. We assume the pink with the ACP and we try to get the blue, and then if we get our done line by CP. And then direct proof, which is actually simpler, which is what we did in geometry. We're trying to prove pink, we do some work and we get pink, and that's by direct proof. That gives us our done lie. Okay, now if you don't understand some of that stuff, you need to go back and review video 3. I'm not going to teach it again. I'm assuming you know these rules coming into this video. Okay, so now predicates, letters, variables, and sentences. So here we are on our outline. Now, in video 3, in Sentential Logic, we worked with whole sentences. The smallest sentences we dealt with were P, Q, and R. We never looked inside of them. We never looked to see what was inside of P. But in predicate logic, we do look inside the smallest sentences, and we do that with predicates and variables. Now, logic is closely related to grammar, and so I need to talk just a little bit about grammar here. Now, a noun in grammar, a noun is a word or a group of words that mean any of these things. It can be a person, like Charlie, a place, like a forest, a thing, like a teapot, an idea, like danger. A verb is a word or a group of words which conveys an action, like walk, an occurrence, like happen, a state of being, like be. Now, let's talk about predicates. In traditional grammar, now what is traditional grammar is the grammar that has been used for hundreds of years to describe how languages fit together, how sentences fit together in a language. A declarative sentence in traditional grammar has 2 parts, a subject and a predicate. And the subject has to contain a noun, and the predicate has to contain a verb. And here's an example. That banana is too green to eat. Well, that banana is the subject, which is not underlined, and I've underlined the predicate, which is too green to eat. These are grammar exercises that children do in school sometimes. Okay, here's another one. David, that's the subject, might be attending the movie. That's the predicate. Here's another one. Austria is between Italy and Czech Republic. Okay, so the Austria is the subject, and the rest of the sentence is the predicate. Now, in transformational grammar, a predicate has a different meaning. Transformational grammar was created in the 20th century. It was a huge breakthrough, and it is so powerful that it can be used. It actually underlies all spoken languages, and it relates directly to the way the human mind processes language. And it can be used by computers. That's the basis of software that translates, like from French to German or from German to Chinese. It's very fascinating stuff. Anyway, the word predicate has a different meaning in transformational grammar. Instead of what we did up here, the old-fashioned way, predicate means a verb and certain other words, and it has blanks where you put the nouns in. So here's one. Blank is too green to eat. Now it looks like this one up here, except that we put a blank where that banana is. This whole thing, including the blank, is a predicate. And then what you need to do to make it into a sentence is you have to put a noun in the blank, like that banana. And then it becomes a sentence. So it's, when it has the blanks, it's a predicate. When you fill in the blanks, it becomes a sentence. Here's another one. Blank might be attending blank. Well, that's like this one up here. If we put David in the first blank and we put the movie in the second blank, then we get a sentence, just like this sentence up here. Here's another one. Blank is between blank and blank. This is a predicate with 3 blanks. Most predicates have 1 or 2 blanks, but sometimes you get 3. You could have as many as you want, actually. And that's like this one up here. So we put Austria in the first blank, and we put Italy in the second blank, and we put Czech Republic in the third blank. Then we're going to get a sentence, which is this sentence right up here. Okay? Now, in predicate logic, so up to, I'm talking here about language grammar. Now, switching to predicate logic, which is the subject of this video. Predicate logic uses the word predicate in the way that transformational grammar does. Not this way up here, this way. So a predicate in predicate logic is this kind. It's stuff with blanks in it. Okay? So, now let's talk about the letters in our logic system. We use capital letters, most of the capital letters, excluding these, for predicates. So, excluding A, B, G, H, P, Q, and R. And we use lowercase letters A through Z for our variables, and the variables represent nouns. So capital letters are our predicates, and lowercase letters are our variables, which are our nouns. except that capital letters P, Q, and R, we're holding those in reserve to mean whole sentences, which is what we used in video 3. So P, Q, and R are reserved for entire sentences. They don't have blanks in them. And then capital letters A, B, G, and H, these are specialized. We'll use them a little bit at the end of video 9, a little bit in video 7. These capital letters are nouns that are not variables. They're what we call constants. Okay, so now how do we make a sentence? Okay, here's a couple of predicates. M. A capital M means blank is a man. A capital L means blank loves blank. Okay, so now here's some variables. Now see, the M and the L are capital letters. Now here the variables are lowercase letters, C and D. So C is going to mean Cindy and D is going to mean Dan. Now to make whole sentences, we have to put the predicate, we put the predicate letter first, and then we follow it by one variable for each blank. So let's look at some examples here. Capital M, lowercase c, what does this mean? This means Cindy is a man, because we put the C into the blank. Here's M is the predicate, it has one blank, and C goes in that blank. So we get Cindy is a man. You see that? Now I think that's false. I've never met a man named Cindy, so it's probably false. All right, here's another example. Capital L, small d, small c. Well, L is the predicate. It has two blanks. Blank loves blank. And D goes in the first blank and C in the second. So it means Dan loves Cindy. See that? Is that true or false? Well, I don't know. Okay, how about this one? Capital L, small c again. This means Cindy goes in both of the blanks. So Cindy loves herself. All right, now this one here, now let's get a little more complicated. We're using some predicate logic, some sentential logic here, because we have an and a not. What does this mean? Okay, the capital L, small d, small c, that means Dan loves Cindy, right? And so it says Dan loves Cindy and this other one, LCD, would say Cindy loves Dan. Cindy does not love Dan. See, this says Dan loves Cindy and Cindy does not love Dan. Okay? How about this one? Has if-then in it. Okay, the MD means Dan is a man. So if Dan is a man, then now LCD, capital L, lowercase c, lowercase d, that means Cindy loves Dan, right? So if Dan is a man, then Cindy loves him. See that? So we'll talk about our three new symbols now. Here we are in our outline. So the backwards E means there exists. The upside down A means for all, or for each, or for every. And the equal sign, well, you know what that is. That means equals. So let's talk about the backwards E. The backwards E is called the existential quantifier. It has to do with existence, and it has to do with a quantity. And what quantity? At least one. Not zero. So now let's look at an example here. We're going to use these same two predicates, M and L, and C for Cindy. But here's a sentence. It doesn't have the C in it. This sentence says, with a backwards E and then the X, and then parentheses, and then there's a sentence inside there. It says, there exists something X, such that X is a man. Right? There exists something X, such that X is a man. Now, that means some man exists. And this is true. How about this? There exists something X, such that X is a man, and X loves Cindy. You see that? There exists something X, such that X is a man, and X loves Cindy. In other words, some man loves Cindy. Now let's look at the upside down A, which means for all. This is called the universal quantifier. What quantity? Everything, the whole universe of things. Using the same predicates and C for Cindy, again, let's look at this sentence. This says, for all things X, X is a man. See that? For all things X, X is a man. In other words, everything is a man. This is definitely false. How about this one? For all things X, if X is a man, then X loves Cindy. See that? For all things X, if X is a man, then X loves Cindy. In other words, all men love Cindy. You see the parentheses, there's parentheses, a pair of parentheses after the quantifiers. A quantifier and then something in parentheses. And what's in the parentheses has to be a sentence. But it can have stuff like the if then or and or those kinds of things to be in there. Okay. And the equal sign, you know this. The equal sign is a predicate. It takes two blanks, one on each side. This is a predicate that's represented by a symbol rather than a capital letter. We have a number of those. So this sentence here says x and y, x equals y. It means x and y are absolutely identical in all respects. They both represent the very same identical thing. All right, so now let's move on our outline here. We'll talk about free versus bound variables. Now we have two kinds of variables. Every variable is either free or bound. I'm talking within a particular sentence. And this is true not only in logic, but in all of mathematics. What a quantifier does is a quantifier captures a variable into bondage. I'll see what I mean by that. Okay, now look at this sentence here. We have, for all x, if mx, then lxc. Now look at, c is free and x is bound. Now why is that? C is free because there's no quantifier there that says for all c or for all, or there exists a c, but there is a quantifier on the x is for all x. So that for all x, that x there by the quantifier is linked to and is binding and capturing the x here under the m and the x there in the L. So the x is bound by this universal quantifier, okay? So in this sentence, c is free and x is bound. Now let's look at this sentence. If mx, then lxc. Well, here they're both free. C is free and x is also free. There are no quantifiers. If there are no quantifiers at all, then all the variables are free. How about here? There exists a y such that stuff in here. Well, here x is free because there's no quantifier on the x. So if we have mx, if mx, then lxy, well, both of those x's are free. But the y is bound. The y is bound by the existential quantifier, see? Now how about here? Now here we have two quantifiers outside the parentheses. We have, there exists a y such that for all x, if mx, then lxy. Now here they're both bound. Both x and y are both bound. The x's are bound by the for all x, and the y is bound by the exists of y. See that? Okay. Now let's compare what the purpose. See, free variables serve a completely different purpose than bound variables. It's very important to know the difference. As a matter of fact, this distinction is a stumbling block for calculus students in high school and college. It's rarely taught, and it's often obscured by sloppy notation. Anyway, now, what are free variables? A free variable represents a value getting plugged into a predicate. So, using this predicate here, mx, this says x is a man. In other words, x is a value getting plugged into the blank in the predicate m. Now, is mx true? Is x is a man, is that true? Well, that depends. That depends on the particular value that x is representing. See, what depends on what x means. What does x represent? That will determine whether mx is true or not. In other words, the truth of a sentence depends on the values of any free variables it contains. You see that? Now let's look at bound variables. A bound variable is a completely different. It represents a linking of a quantifier to a blank in a predicate, or maybe blanks in several predicates. How about this? For all x, mx. This says everything is a man. What does the x do? The x links the universal quantifier to the blank in the predicate m. Now, is this true? For all x, mx. Is that true? Everything is a man. Is that true? That is definitely false. It does not depend on any value of x. It's just categorically false. I don't care what x is. This sentence here, is false. What matters is the linking. What matters is the fact that the x is linked to a universal quantifier. That's what makes it false, is the linking, not the value of the variable x. How about here? For all y, my. This also means everything is a man. Because the quantifier linking is the same here as it is here up here. We're just doing it with a different bound variable, y instead of x. How about this? There exists a z such that mz. This says something is a man. Well, this is definitely true. Z links the quantifier, the existential quantifier, to the blank and M. All right, now let's move on in our outline to multiple variables in the same sentence. So if we put free and bound variables together, then the truth of the sentence will depend on the values, this is a review, values of the free variables in the sentence and the quantifier linking of the bound variables, okay? So here are three predicates. We got man, woman, and loves here. And let's look at this sentence here. What this sentence says is, there exists an X. See that? Such that X is a man, and X loves Y, and Y is a woman. You see that? In other words, some man loves Y, and Y is a woman. Now in this sentence, X is bound, and Y is free. Now, is it true? Is this sentence true? It depends only on what Y is. It doesn't depend on what X is. It's true if Y is a woman whom some man loves. It's false if Y is not a woman. It's also false if Y is a woman that no man loves. You see that? Okay? Depends on what Y is. Now, what happens when we put quantifiers inside of quantifiers using these same predicates? Look at this sentence here. You see that X and Y are both bound. Look here. It says we have on the outside there exists an X, and I'm using the square brackets to avoid confusion with the nesting, where you do nesting within a sentence with parentheses and also square brackets to see how the grouping is going. Okay, so we have exists an X out here, and then we have MX and now look in here, we have for all Y, and then in parentheses, WY implies LYX. X and Y are both bound, you see. The X is bound by the existential quantifier out there, and the Y is bound by the universal quantifier that's here, right here, see, inside. In other words, this says there exists something X, such that X is a man, and for all things Y, if Y is a woman, then Y loves X. What does that mean? There's a man who, for all things Y, if Y is a woman, then Y loves him. In other words, there is a man whom every woman loves. See that? See how that works? All right. Now, is this true? Probably not. I don't know of any man who every woman loves. But whether it's true does not depend on Y or X. Whether it's true only depends on the linking structure because they're both bound. All right, so now we're done with talking about our new symbols, and let's move on now to our new rules of logic and our example proofs. So we're going to start by working with universal quantifiers. Here we are in the outline. We're going to start with logic rule 10, which is called universal instantiation. Now here's what it means in a nutshell. What is true for everything is true for any given thing. Let me explain this. Suppose we know, hypothetically, everything is a frog. Obviously this isn't true, it's just a fun example. Supposing we know that everything is a frog. Well, that means that we know that any given thing is a frog, right? Now, what about M? Yes, M is a frog. If everything is a frog, then M is definitely a frog. How do we get that M is, from going from everything is a frog to M is a frog, how do we know that? This is by universal instantiation, which is UI. We're going to use that rule lots of times. M is an instance of a frog. In other words, we've taken the universal statement that says everything is a frog, and we take an instance with M. Okay, M's a frog. Okay, now, what about K? Well, yes, K is also a frog. Why? This is by UI. Okay, how about Y? Yes, well, Y is also a frog by UI, right? And so let's take an example here. We'll let this predicate F mean blank is a frog. All right, again, supposing we know everything is a frog, now how would we write it? We would write it this way. For all x, fx. Now, x is a bound variable, bound by the universal quantifier. So since x is bound by the universal quantifier, that means that what we can do with this rule, ui, we can strip off, this is in the middle of a proof, we're going to do this. We can strip off the quantifier and plug any free variable in for x and infer, like here, fr. In other words, r is a frog. So we can go from this sentence in a proof to this sentence. So we can, for all x, fx, we can say fr. Why? This is by ui. And we have to make sure that r is free. We can also get fx. X is a frog. Or fz. You see, fx, even though x is the bound variable here, we could use it and get fx as the free variable by ui, or fz. So what ui does, it removes a universal quantifier, it exposes the statement inside, this fx, and then changes the bound variable to a free variable. Here's what it looks like. We have a sentence here, this yellow sentence, and this yellow sentence has for all sign, and then a blue dot. The dots now mean variables. In these signs, in these rules, when I have little dot, colored dots, they mean variables. So we have a variable, a blue variable, and then parentheses, and inside the parentheses is this pink sentence. And inside the sentence, the variable appears in some places. From there, we can get the same pink sentence. We can strip off the for all, and we get a different variable in those same things. Now it becomes red. It could be any free variable. It could also be the same variable as the blue one was, if we want. But the red variable has to be free. This is universal instantiation, and when we do the proof, you'll see how it works. Okay, so now let's move on to our next rule, Rule 11, called universal proof. Now, I'm going to give an example from geometry here to help you understand how this works. Now, the isosceles triangle theorem, here we're switching back to geometry. Here's what it says. In any triangle with two equal sides, the angles opposite those sides are also equal. Now, look at this diagram over here. Here we have two sides. The two sides of this triangle are equal. What the theorem says is that the angles opposite them are equal. See these? How about this triangle in the middle? It also has two equal sides, and the theorem says that the two angles are equal. And this one over here again has two equal sides, and the angles again are equal. These are three completely different shaped triangles. Now, how would we prove? How would we prove the isosceles triangle? In order to prove it, here's the principle. We don't need to do a separate proof for every triangle. We don't need to prove it for this triangle and this triangle and this triangle. There's an infinite number of triangles. You don't have to do an infinite number of proofs to prove this. All we have to do is we need to prove it for one triangle that is an arbitrary triangle with two equal sides. In other words, this is the proof we need to do to prove the isosceles triangle theorem. Here's a diagram. Given AB equals BC, prove angle A equals angle C. As long as this diagram is arbitrary, if this is a typical isosceles triangle, then by doing this proof for this arbitrary isosceles triangle, we automatically prove it for all isosceles triangles. Why? Because we could just replicate the same proof over and over. Whatever triangle you take, do the same proof on that one. And so if it works for an arbitrary triangle, it will work for any triangle. So what universal proof says, it says if something is true for an arbitrary thing, then it is true for everything. So supposing we want to prove for all x, fx, in other words, we want to prove that everything is a frog, we're never going to be successful. We'll say we did. We don't need to do a separate proof for every single thing. All we need to do is do the proof for one thing that is arbitrary. In other words, if we can prove fx where x is an arbitrary x, if x is arbitrary, okay, then we've done it. Now the rule is to ensure that it's arbitrary is the variable x cannot be free in any previous line. So if we can prove fx for an arbitrary x, then we could replicate that proof for anything. This is called universal proof, or UP, and it's our third type of proof, and along with CP and DP. And what UP does is it adds a quantifier to a statement and changes a free variable to a bound variable. So here's how the rule will look at our proofs. Let's, if we're trying to prove, we have a prove line, a claim. And the statement is a universal statement, meaning it starts with for all something, for all x, for all y, the blue dot. And then something in parentheses, this pink statement in parentheses, that has the blue variable in it somewhere, or maybe several places. Here's what we do. We write the prove line like this. Now, we have to make sure that that blue variable is not free anywhere up here. That's very important. Because if it's free up there somewhere, then it's not arbitrary. Okay? To guarantee that that blue variable is arbitrary, it cannot be free up there. It can be bound up there, but not free. Okay. Then we do some work. And then we see if we can get the pink statement with the blue variable in it, like this, without the quantifier. If we can do it, then we proved the pink statement is true for an arbitrary blue variable, and that means it's true for all of them. And so then we get to write done, and we put UP, meaning universal proof, and then we get to box and cancel the proof like that. So that's how universal proof works. Okay. So now let's go on to our next, it's actually our fourth. We did 3 example proofs in video 3. This is proof number 4. We're given this, we have to prove this. So we're given for all x, if fx, then kx. Prove if for all y, fy, then for all z, kz. See that? That's what we're doing. So we're going to use 4 columns as usual. We're going to start with the claim rule as usual. We're going to try to prove that we're going to write something we have to prove, and it's by the claim rule, and we're trying to prove the very thing we're trying to prove, right? This is just like in video 3. Okay, and continuing as in video 3, we can see this is a conditional. We're trying to prove pink implies blue. Now I realize it has some new symbols in there, but the structure of this statement is a conditional. The outermost statement is still a conditional. And so we're going to do a conditional proof. We're going to assume the pink, and we're going to try to get the blue. And I'm not going to put conditional proof up there, the rule. I'm not going to put modus ponens up there. I'm not going to put repetition up there because I'm assuming you know those rules already. Okay, this is our assumption for conditional proof. And now what? Well, I'm going to use the claim rule again, and I'm going to say I want to claim this. That's by the claim rule. And why did I pick that? Because that's my goal in the outer proof. Now, I talked in video 3, and I'll talk about now, we talk about nesting proofs inside of proofs. I also use the word nesting, I use it horizontally and vertically. When I talk about horizontal nesting, I'm talking about parentheses and parentheses inside of parentheses, statements inside of statements in a single line. When I talk about nesting proofs, I'm talking about vertical nesting. Okay, this proof, which is a collection of things, is nested inside of this proof. So there's vertical and horizontal nesting. In any event, this is now I'm nesting another proof inside of this proof. This is vertical nesting. Okay. All right. And now, what kind of thing is this that I'm trying to prove? I'm going to use my universal proof rule, because look at this thing I'm trying to prove. It's a statement of the form. It says, I'm trying to prove for all z, kz. That's like this. It has a universal quantifier, and then now the z is the blue. The blue dot is the variable z. And inside the parentheses is this pink statement, which has a z in it, kz. That's like this right here in the rule. All right? But what do I have to do? I have to make sure that z is not free up above. Do I have any z's up here? As a matter of fact, I do. I have a couple of z's right up here in line 1. But is it free or bound? It's bound. This z is bound by that quantifier there, see? So it's not. Do I see any other z's up there? No. I'm okay. I'm good to go because z is not free up above line 3. So I can proceed now, and what I need to do is I need to try to get this statement in here all by itself, like that. I need to try to get kz all by itself without the for all z out in front, okay? All right, so now what? Well, right here, look at this line 2. What I'm going to do with line 2 says for all y, fy. I'm going to use this rule, universal instantiation. And what I have here in line 2 is like this. Now look, y is now, remember I use the colors and then I take them away, and I use the colors and I take them away because the proof itself is all black and white. And every time I use the colors, I use them differently. Okay, so now the blue variable is y, and the pink statement is fy. You see, and I have for all y, fy. That's of this form here. You see that? The yellow statement, and then what it says is for all blue variable, and inside parentheses, some pink statement that has a blue variable in it. That's just like this. That means that I can do this. I can, watch, I can write FZ. I know that everything F's. That means that Z F's, right? If F means a frog, if everything's a frog, then Z's a frog. So what I did now, as I used the variable Z, I put the variable Z in where the Y was up here to get FZ. You see that? Now, is Z free here? Yeah, as long as it's a free variable, which that's virtually always going to be the case. That's not going to be a problem. Okay? And what does that come from? That came from line 2 by UI. See, now we just used UI for the first time. We're going to use it a lot of times. Okay, now what? Well, let's go up and let's grab our given. We have a given up here. Let's bring that given in by repetition. And now let's look at this. This statement also has a universal quantifier. This is the outermost statement is a universal statement. For all x, stuff inside. Well, I'm going to use my rule UI again. And this time, though, the variable is going to be x. Okay, I have for all x, and in the parentheses I have a pink statement, just like this. See how this looks like this? Same form, okay? And I have a pink statement with x's in it. This time there's 2 x's in there. All right? That means that I can put any variable I want in for x. And what variable do I want? I'm going to pick z. I'm going to put z in where the x is. See what I did? I took this here in the pink statement, wherever the x was, I changed the x's to z's. You see that? And where did that come from? That came from line 5 by UI. See that? All right. Well, now look. I have FZ, pink here. I have pink implies blue here. This is FC. This is if FZ, then KZ. Well, then that means I can get the blue, right? This is by 4 and 6 by modus ponens, right? All right. Well, look. Well, I was trying to prove, using the universal proof, I was trying to get what's inside the parentheses up here with the blue variable free. Well, look what I did. I just got it. I have KZ here all by itself. The Z is free there without the quantifier. That means I proved KZ where the Z was arbitrary. And that means I'm done. That means I've proven for all Z KZ. See that? And where does that come from? That comes from line 7 by UP. See? See, that Z is arbitrary. And that gives us the right to box and cancel the proof. So there's our first universal proof, which we just did to show that for all Z, KZ, everything K's. I don't know what K stands for. It doesn't matter. Okay? All right. And now that we have that, well, that was our goal in the outermost proof, which was we're trying to prove pink implies blue by a conditional proof, and we assumed the pink, we got the blue. That means we're done with that one by CP, from 3 by CP. That's just sentential logic like in video 3. And I popped the indentation level out on the done, okay? And so now I get to box and cancel this proof, and there it is. So that proof is done. All right. So now let's move on and talk about existential quantifiers. So here we are in our outline. We're going to look at 3 new rules, and we're going to do another example proof. Existential instantiation. This is our next rule. So supposing I'm going to change F. Instead of talking about frogs, let's talk about France. Okay? F means blank is a person who was born in France. Okay, now suppose we have 3 people. We have Thomas, Rebecca, and Veronica, and T, R, and V are those variables are going to stand for that. So T is Thomas, R is Rebecca, V is Veronica. Now supposing we know this pink statement here, someone was born in France. Now from that, let me ask you a question. Can we infer that R was born in France? In other words, can we infer that Rebecca was born in France? If we know that someone was born in France, does that mean that Rebecca was born in France? No way! Okay, just because someone doesn't mean Rebecca was. So I can't put R in there. But what I can do is I can let the someone that was born in France be a brand new variable, like B. I can say B was born in France. And this is by existential instantiation. It's an instance of this statement here. I know someone was born in France, so I can let something be it, but it has to be a brand new variable. B is not listed here. I don't have B anywhere there. B's brand new, so it's okay to say, okay, well, let's let B be someone who was born in France. You see how that works? Now let's do it again. Let's talk about what is the principle. The principle here is what is true for something must be true for some particular thing. So supposing we know someone was born in France, okay, exists in X, fx. If we know that, that means we know some particular person was born in France, right? And we can let that person be represented by a brand new variable b, and that would be fb. And this is by existential instantiation, EI. B is an instance of a person who was born in France. But if the variable r is already in our proof, in other words, it has some meaning on it, like Rebecca, then we cannot use EI to say FR. Whatever we do, we have to have a brand new variable. And what EI does is it removes the existential quantifier, exposes the statement inside, and changes the bound variable to a free variable. It's like UI in that sense, but the rule is much more restricted. UI, I can put anything in. EI, I have to put a brand new variable. Here's the rule. So here's my statement with the existential quantifier. So I have exists a blue variable such that, in parentheses, I have some pink sentence here with hedges of blue. That means that I can write down the pink statement without the existential quantifier, putting a red variable in, but the red variable has to be a brand new variable. Okay? All right, now let's look at the next rule, number 13 here, existential generalization. This is e.g. What this says is what is true for a particular thing is true for something. So, supposing that V means Veronica, variable V, and supposing we know FV, in other words, Veronica was born in France. Now V is free here. V is a free variable here. So we know that Veronica was born in France. That means we can infer that someone was born in France. You see that? We can infer that there exists an X, such that X was born in France. Something was born in France. Someone. And this is by existential generalization. We're generalizing the fact that Veronica was born in France to say that someone was born in France. So e.g. adds an existential quantifier to a statement and changes a free variable to a bound variable. You see, here the V is free, and here the X is bound. We can pick any variable we want for the bound variable. Okay, now here's what the rule looks like. So I have a statement up here with no quantifier, it's a pink statement, with a red variable in it, and the red variable's free. Then what I can do is I can stick on an existential quantifier with a blue variable and change the red variables to blue variables like that. You see what that means? All right. Now our third rule is called substitution of equals. That's actually third in this little section. It's rule 14 in logic that we're doing. Okay? So substitution of equals, SE. Now we did this in geometry. We used a special simplified form of substitution of equals in geometry. Now we're going to use it in its full power. All right, supposing we know these two things. We know that Mark Twain wrote The Adventures of Tom Sawyer. Supposing we also know that Mark Twain equals Samuel Clemens. Well, then we can say that Samuel Clemens wrote The Adventures of Tom Sawyer. You see that? In other words, what I can do, since I know Mark Twain is equal to Samuel Clemens, and I have Mark Twain sitting up here in this sentence, I can stick the Samuel Clemens in where Mark Twain is up there, and that's how I get this. You see that? I substituted it in. This is by substitution of equals. Two things are equal, I can substitute one of them in for the other. Okay. So supposing we know these two things. We know fx implies mw and nx. That's one thing we know. The other thing we know is that x is equal to y. Well, that means that we can plug the y in where the x is. there's actually two x's here. We can plug it in both places, and that means we know this. Fy implies mw and ny, and this is by substitution of equals. Now, nothing happened to the w. I left the w alone because I don't know anything about it, but I know x equals y, so I was able to plug the y in where the x's are. But the x and the y have to both be free variables. You can't play this game if there's some quantifier out there that's binding them. Okay? So here's the rule. I have two statements, and that's what two arrows. Substitution of equals requires two lines of numbers in the reference column, in the for column, the by column, the from column. Okay, so we have a statement here in pink with a red variable in it, and then we have another statement that says that the red variable is equal to the blue variable. Then I can rewrite the pink statement with the blue variable there instead. See that? And they both have to be free variables. Okay, so now we're ready to do our next logic proof, which is proof number 5. Okay, so we have a given and a proof. They're both a little bit complicated. I'm not going to talk about them now. I'll talk about them as we get into them. So we're going to have 4 columns, as usually, as we always do. We're going to start with the claim rule. We're going to claim, by the claim rule, the very thing that we're trying to prove. So now let's look at this just a little bit. What is the outermost statement here in this thing that we're trying to prove? We have exists in x, fx over on the left, then implies, and then for all y and a bunch of stuff in square brackets over here. So what's the outermost statement? It has to be this implies sign right here, doesn't it? Okay, so that means we have pink implies blue that we're trying to prove. So we'll do that with a conditional proof. So we'll assume the pink by ACP. And we'll try to get the blue. All right, so now look at this statement here in line 2. It says there exists in x, fx. So something f's. We can use our new rule, existential instantiation, EI. And what we have here in line 2 is exactly in this form. You see, I've got x is the blue variable, and inside the parentheses is a pink sentence with x in it. Okay, it's just fx, although I know there are 3 dots here and only 1 up there in the pink. That doesn't matter. Okay, and so that means we can produce the pink statement with the exists in x gone like this. We can strip off the quantifier, but we have to put in a brand new variable, a. There's no a anywhere up here in the proof. A is brand new, so by putting a in there, I'm okay. It's a brand new variable. That's the red variable, okay? And this is from line 2 by EI. All right, now I'm going to use the claim rule again, and I'm going to write prove this thing by the claim rule. And why did I pick that? Because that's my goal here in the outer proof. See, I'm trying to prove that thing, so let's copy it down and see if we can prove it. Well, what form is this statement? It says for all y and then a bunch of stuff in brackets. What's the outermost statement? It's a universal statement with the universal quantifier. So to prove that, I have to prove that. To prove something that starts with a universal quantifier like that, I need to use universal proof. Which means, so I've got a statement here of this form. I've got for all y, and then in the parentheses, or brackets in this case, I have a pink statement that has y in it. That's if this form like this, you see. Now I have to make sure that variable y is the variable that is the quantifier. That's what I have to make sure that it's not free up above. Do I have any y's up there? I do. I have a couple of y's right here. Free or bound? It's bound. It's bound right there. The y and the ky is bound by that for all y. Are there any other y's up here? Nope. So I don't have any free y's. See, blue variable can't be free up there. I'm okay. I'm good to go. So in order to prove this universal statement, I have to prove it without the quantifier for an arbitrary y. I know y is arbitrary because it's not free up above. So I have to try to prove this thing here, like that right there, okay? So now I'm going to use the claim rule again, and I'm going to write prove, in fact, by the claim rule, what am I trying to prove? This very thing. I'm trying to prove this thing with the y free. See, y is free in line 5. In line 4, y is bound. In line 5, y is free. All right, now What's the form of this statement? The outermost out. ky implies then have exists a z and stuff in there with z. Well, the outermost statement is the conditional, isn't it? Which means I'm trying to prove pink implies blue. To prove a conditional, I use CP, conditional proof. So I had to assume the pink. So I'm assume ky. That's my assumption for conditional proof, right? Now I'm going to try to get the blue. All right, the blue says there exists a z such that fz and kz. So fz and kz, something f's and k's. All right, so now look what I'm going to do. I have fa here and I have ky there. I've got af's and yk's, if you will. Well, I'm going to use my rule adjunction from video 3 by saying if I have pink and I have blue, then I can say pink and blue. I'm going to do that. I'm going to say fa and ky. Where did I get that from? Lines 3 and 6 by adjunction, right? That's from Sentential Logic. And now this here, this line 7, is looking a little bit like what I'm trying to prove. A little bit. But now watch what we're going to do with this. Okay, we have a given up here. We're going to bring that given down now by repetition from the given, okay? And now look at the form of this given. It's got for all s, for all z, and then stuff in brackets. In other words, the outermost statement here is certainly a universal statement. So what I can do is I can use my rule UI on this, but I've got to do it one layer. I've got 2 layers. I'm going to have to do it twice. I'm going to do it in 2 steps. First, I got to deal with the s. I have for all s, and now look what here I've done here in pink. The for all t is part of the pink. What's inside of that for all s is the whole thing, for all t and everything to the end from there. Okay, that's like this. And the blue variable is s. So there's a blue s by the f there, and then on the left side of the equal sign over on the right-hand side, that's also an s. There's also a couple of t's in there. I'm not touching the t's. I'm dealing with the s right now. And so what I'm going to do is I'm going to plug something in for the s. And what I'm going to do is I'm going to pick, I can pick anything I want, I'm going to pick a. So what I did now, the red variable is a. What I've done is I pulled off the for all s on the outside, see that? And what remains is the pink part without the for all s. And I have put the variable a in, that's the red. So the blue up here, the blue s became a red a there. The blue s there became a red a there, see? And where did that come from? That came from line 8 by UI, all right? Now we're going to do it again, because we still have another universal quantity. We have for all t. So we'll use UI another time. This time we're doing it on t. All right? And so I have for all t, and then the pink statement. Now the pink statement is a little shorter. Now it's just the part that's inside the brackets there. And I've got t over here with the k, and a t on the right-hand side of the equal sign. And so what I'm going to do, I can plug something in for t. And I'm going to pick y. So what I did was I put a y in where the blue variable, I stripped off the for all t, and now I have kt there, I changed that to ky. On the right hand side of the equal, I changed the t to a y. See that? And where did that come from? That came from line 9 by ui. All right? Well, now look. In line 7, I have fa and ky, and down here I have, this is a universal statement, a conditional, isn't it? I've got the fa and ky in parentheses, implies this equation, a equals y, that's also in parentheses. So the outermost statement here is a conditional. So I've got pink, and I've got pink implies blue, so I can use modus ponens to produce the blue, okay, on the right-hand side there. And where did that come from? Lines 7 and 10 by modus ponens. All right, now, we have this rule substitution of equals. And what I'm going to do, let's look here. Look at these 2 lines, 7 and 11. Line 7 is like this one right here. In line 7, I have something that has a y in it, and the y is free, by the way. And down here in line 10, I have a is equal to y. Well, if a is equal to y, then I can put a in where the y is up here by substitution of equals, see? So what I'm going to do now is I'm going to copy line 7 down, but I'm going to change the y to an a because I know that a is equal to y. And that comes from lines 7 and 11 by substitution of equals. You see that? All right, now, I'm going to use this rule existential generalization. Look what I've got now. I've got FA and KA. Now they're both A's. Something F's and the same thing also K's. This is getting very close to what I'm trying to get in line 5, but I'm not quite there yet. I need this rule. I need to use existential generalization, which says that if I have a statement here like this, where I've got this pink statement with a red variable in it, it's appearing twice, that A, the A is the red variable, and it's free, then I can stick on an existential quantifier. I know that A does this thing. That means something does it, right? So I can write, and I can pick any variable I want. I want Z. By the way, the reason I want Z is because I'm looking up here at line 5, okay? I want a Z. I want to use Z for my variable, my bound variable. So I get exists as Z, and now inside here, I change the two red variables, which are A's, to Z's. That's exactly what happens here. Here I have A, both F's and K's, and now I say something, both F's and K's, right here. Where did that come from? That came from line 12 by e.g. You see how that rule works? All right? And now what? Well, that's exactly what I'm trying to prove. Just exactly like that. I was this third level proof here. It started on line 5. As I've got I got a main proof and then a proof nested in that and another proof nested in that. That innermost proof was a conditional proof. I assumed, I'm trying to prove that pink implies the blue. I assumed the pink. I got the blue. So that means I'm done with that proof. And that's from line 13 by conditional proof, CP. So I can box and cancel that innermost proof. Okay, and now what? Well, let's look back at what we're in the middle of. Our middle proof, the proof that's happening from line 4, that's a universal proof. See, I'm trying to prove for all y stuff in the brackets there. Well, I'm in the middle of using universal proof. I'm trying to prove this. I need to get the thing that is in the, let's see, here, look at, okay. I'm trying to prove, I have to try to prove this pink statement with the blue variable free, right? And so, well, look what I've done. I've done just exactly that here. In line 5, I've got the pink part that's in line 4, without the for all y out in front of it. I've done it with the y free. In other words, I have proven this is true for an arbitrary y. If it's true for an arbitrary y, then it works for anything. That means that I'm done with the proof that started in line 4. Okay, getting a little complicated, but you can handle it. Just keep watching. All right, and where did that come from? That came from line 5, where I reached. Where I reached the goal in my universal proof, which is to prove the thing for an arbitrary thing without the quantifier. I got that, and so this is from line 5 by UP. That means I have done. I can box, and I popped out the indentation on the done, and so I can box and cancel that proof. Okay. And now, if we remember, the outermost proof is a conditional proof. I'm trying to prove pink implies blue. I assumed the pink. I just proved the blue, because line 4 is exactly the blue there. And that means I'm done with that outermost proof. And where did that come from? That came from line 4, right, where I proved that the proof is canceled out by CP. And that means I can box and cancel this proof. I want to make one remark before I forget, which I've been meaning to make in these videos. When you box and cancel, when you do a box, you're not allowed to have any uncanceled proof inside the box. See, I just drew a box, this big box here, and it has line 4 has a proof in it, but the proof is canceled. It's okay to draw a box around a proof that's canceled out, but if you can't draw a box if there's an uncanceled proof inside. Okay, so I'm done with this proof. All right, so now what we're going to do lastly is we're going to compare these four rules, the four rules involving quantifiers. So just take a look at how they all fit together. UI, EI, and EG are each inference rules. An inference rule, meaning we have some statement and then we produce a new statement from it, okay? By one of these three. UP, on the other hand, is a proof-ending rule. You can't just have a statement and from that statement get, oh, well, everything does it. No, you have to do a proof using UP to prove a universal statement. And so that gives you a right to say done. Okay, so this little table right here, let's just compare these. Okay, in the two columns, no, in the two rows, this row is for the universal quantifier, and this is for the existential quantifier. So these two rules, UI and UP, are for the universal quantifier, the upside down A. And these two rules here are for the existential quantifier, the backwards E, okay? Now look at the two columns. The column on the left, what it does, these two rules, UI and EI, they each remove a quantifier and free the variable. And these other two on the right, UP and EG, they each add a quantifier and capture a variable. See how they all fit together? So we can do all these different maneuvers that we need to improve in proofs. But there are very exacting rules about what makes sense to do and what doesn't. And I've tried to teach that to you in these videos. Okay, so that takes care of our video 4, part A. We've explored how quantifiers work now. And we're going to use all this quantifier logic when we do our proof that God exists. We're in videos 6 and 7, when I talk about the axioms, we're going to use quantifiers. They're quantifiers in the axioms. You need to understand quantifiers to understand what the axioms are actually saying, and also the definitions. And then also our informal proof. And then when we get to video 8, we're going to be actually doing a proof with just this very kind of stuff in it. Okay, so that takes care of video 4. Here's the whole map of the videos. The next video is video 5, where we're going to continue, and I'm going to talk about uniqueness, and we're going to add 2 new symbols. And so I hope to see you there in video 5. I'm Mark Lawrence Donald Emerson.